My name is Vlad. This is my colleague Andrew. We're Facebook engineers on the browser engineering effort at Facebook. That's a thing. So we're going to talk about some of our insights about JS parsing costs. We're going to talk about, how do I click this? How do the advanced slides?
Arrow keys.
I'm trying. There we go. That does it. So we're going to talk about why parsing costs still matter despite significant improvements in recent Chrome releases. Some of the measurements we did and our insights from it, and then some potential solutions about what you can do, what sites can do to make these parsing costs lower and get better startup costs and better interactions, as well as an update on this experimental effort we've been working on called BinAST. So why do parsing costs matter? So 100 CPU milliseconds on a critical path during page load, and it's only like 2 to 7% of the main thread execution time during startup, so it's not like the biggest cost or dominant cost. Compilation is actually worse than parsing, although they're tightly related. There's other things like execution time, styling, layout, all those kinds of things. But it's still significant. It's still a big part of the cost. And because Facebook cares a lot about the startup cost, it started investigating server-side rendering technology, where you actually render the page first on the server for every user and then send it down as HTML and rehydrate it. So this startup cost is very important to us, and parsing is one component of it. Additionally, when you have any sort of interaction, because we're a website that's pretty well optimized and tries to follow best practices, we load code dynamically. So when you load code dynamically, that means you need to parse it, you need to compile it before you can execute it. So all of these JS overheads happen on a critical path and are very visible to the user. And then, of course, compilation is driven by what is parsed. So you have to make sure you parse just the right amount of things. Otherwise, you're going to be doing extra parsing and compilation work, which is pretty bad. So what are the components of parsing cost? In our measurements, we find that CPU single thread speed is really what determines how long it takes to parse something. It's not really the number of cores available. It's really just single thread speed that determines how much CPU time it takes. Of course, that time is kind of variable because you have heat, you have battery conservation, you have slow cores, fast cores, so it's not super straightforward. So it's really important to measure on real devices, not our developer desktops. As background, people who might not be familiar, although I recognize a lot of V8 team faces here, there's two kinds of parsing. There's pre-parsing, which is really fast, and it's mostly correctness check. This is what's called a syntax parse, and does not build an AST. And there's a full parse, which is slower. It builds an AST, which can then be used to compile things. And you can, if you're unlucky, the engine will do a pre-parse for the same code, and then later on do a full parse when it actually needs to execute it. You can trick it to just do the full parse right away by putting like parentheses around your function declarations to make it look like it's about to be executed. So that triggers a full parse immediately. So this is kind of like a lever that you as a website can influence to determine what kind of parsing happens for your code. And of course, there's main thread parsing, which is what we care about, which is the critical path parsing. There's background streaming parsing. V8 has gotten a lot better at this recently. So there's a ton of streaming parsing happening, moving that parsing overhead off the critical path. So as I said, parsing in V8 has really gotten a lot better. There's lots of streaming happening, lots of parallelism. It's not blocking on the main thread. Raw throughput has improved quite a bit, including the scanning speed. And raw parsing is more or less faster than network speeds. When we measured this out of curiosity on our MacBook Pros, they're pretty nice, i7s. We saw like 60 megabits per second parsing throughput. Of course, comparing to network, like wire over the wire costs, you still have to divide by 4 because those are compressed bytes versus parsing uncompressed bytes. So it'd be more like 50 megabits per second, but it's still very fast. However, what we find is that when you load Facebook.com, which is it's a large site, it's like 10 megabytes of JavaScript, 10 to 12 megabytes of JavaScript on startup, uncompressed cost. The main thread does get saturated, so whatever core that thread is on is really like CPU bound. It's not network bound. So what happens is when the JS bytes are coming in, they're getting parsed on those streaming threads. That's going really fast, and those cores are not that busy. However, the main thread ends up doing a lot of parsing, nevertheless, and that parsing is contributing to the fact that it's CPU bound. It is on a critical path. So why do you parse on the main thread when you have these beautiful background parsing threads? In order of increasing importance, inline scripts. Inline scripts are not streaming parsed. Inline scripts show up in the Facebook example where we actually stream down data, like JSON payloads in a document. And those need to be parsed before they can be consumed. And then Inline scripts are also show up when you insert some dynamically loaded code. So you send a network request, you get back some JavaScript, you put it inside the script tag, and then that kind of wires it up to all its dependencies, and it runs when it's ready to run. So that's why that's where inline scripts trigger main thread activity. Small scripts, I think the threshold in V8 is 30 KB wire size. We have a whole bunch of small scripts, like really a lot of small scripts on Facebook.com. Other sites on LinkedIn are a little bit better about that, but in terms of like CPU milliseconds spent parsing on the main thread, that's roughly 45% of where the main thread parsing comes from. And then finally, delazification, which is really just lazy parsing, is a term we made up. That's, you pre-parse on the background thread, and then based on the execution path you actually take through the file, you end up needing to execute different functions, and so you parse them and compile them and execute them lazily. So that's actually the biggest component of cost. And we looked at other websites. It was kind of a similar breakdown. Delazification was always the big one. So this is why, despite these improvements in background streaming parsing, the main thread still ends up spending hundreds of milliseconds, CPU milliseconds, parsing. So Adi Osmani had a nice talk at the Chrome Dev Summit this week. He talked about the performance gap on mobile. So these are like the top 10 smartphones in the world. So you see massive differences between single thread performance of the high-end phone versus the low-end phone. And we also tested on some phones that don't even show up here. They're much worse. But there's still a lot of like sort of like actual parallelism. There's still 4 cores available. So it seems like the CPU power at least is there. Cores just not very fast oftentimes. And then on desktop, things are a little bit better, but these are like the top selling laptops on Amazon. But there's a huge difference between like the really high-end stuff that we all develop on, the MacBook Pros, and then the stuff that consumers actually have. So if you're looking at parsing costs on your MacBook, you're probably not going to see a ton of parsing time on the main thread. But if you're using like consumer, retail hardware, that cost is definitely going to show up there. In absolute terms, it will be significant. So I'm going to turn it over to Andrew to actually talk about some of the measurements that we found and the insights we gleaned from that.
Cool. Right. So yeah, Vlad talked a little bit about like the relative like proportions of where we spend time parsing in the first place. Let's look at some actual data now. So starting from the best case possible for fellow developers, you probably have a pretty beefy machine in front of you right now. Desktopfacebook.com takes around 4.5 seconds to load on that machine. Of this time, 250 CPU milliseconds are spent purely main thread parsing, a third of which is pre-parse. So this is parsing that's almost always blocking execution. With regards to background parsing, an extra 200 CPU milliseconds of that gets deferred and does save the main thread from some extra work. So not terribly bad. Let's make things worse. Mid-end laptop, this is like Ultrabook from around 2016. This took 400 CPU milliseconds on the main thread. And you see that it stays around the same like proportion on the background thread as well. And like the same time distribution of delazification, small scripts, and inline scripts stays fixed irrespective of which device we're executing on. Moving down to low end, we hit 450 CPU milliseconds. And onto mobile, we introduce an interesting aspect here, the dualism of having both a mobile site and a desktop site. The mobile site ships less code. Not always possible for a lot of web devs to make a mobile site that's almost like, it's incredibly distinct and is able to serve less code, especially because many mobile sites are responsive. And it does do a better job parsing less code. So you see around 200 CPU milliseconds on the mobile Facebook and a whopping 600 on desktop Facebook. On a low-end phone, things get pretty hairy, hitting 450 CPU milliseconds on the main thread and 1.6 seconds on desktop Facebook. So is it our fault? Well, probably not. So we're around in the middle of the pack from some of the sites that we surveyed for main thread parsing time. And it seems that people do, as like the needs to serve more JavaScript increase, need to parse and compile more code.
So I'm just going to point out the scale here, which I think is like really faint. So the first line is 200 milliseconds, so each line is an extra 200 milliseconds. So yeah, Facebook is 400 milliseconds on an i5 laptop, and Yahoo at the top is close to.
Another interesting use case are enterprise sites, which are true web applications in every sense of the word. These are very sophisticated, very complex pieces of software that have a ton of functionality and as a result need a ton of JavaScript. 45 megabytes, as it turns out, was the number for Facebook's ads manager. This takes 9 seconds to load, and almost a second of that is spent, or almost a second of CPU milliseconds is spent on the main thread parsing. Another case that's kind of interesting to describe a trade-off with parallelism is interaction performance. So as Vlad mentioned, like a lot of code is executed or compiled lazily. So you might not need all of the code to click on the notifications jewel until you actually click the notifications jewel. What does this mean in practice? It means that you're doing a bunch of parsing right after the user has provided like their intent to open something that is blocking execution and increasing the latency of the interaction. So it's always on the critical path when it's like delazified. So for example, when you click the notification jewel on Facebook.com, for a concrete example, it's 35 milliseconds of main thread parsing time spent on the ultrabook that we described earlier. No background parsing in V8 is currently performed right now. And if you were to naively just like throw it on a background thread, it wouldn't really solve the problem, since you'd just be blocking on that thread's completion before you could show or execute any code. So yeah, as I described, parallelism comes with a few trade-offs. So on one hand, if we increase through the iffy trick that Vlad mentioned, the amount of code that's parsed in parallel, we might not actually need all of that. We could be wasting memory for all the extra bytecode that we generated from parsing and compiling that unused code. We could be wasting battery, and contention and like lack of available parallelism, if there's like other things running on the device, could mean that we're slowing down the main thread and making everything very bad. However, if, as I described with the notifications case, we do too little speculative parsing, we end up delegating a lot of work that we could have done during our free cycles over to runtime. This is a classic like problem of serving only the code that we want to execute, or serving and parsing. So what are some solutions? We could just be smarter, right? So if we know what's going to run on every single startup, we could use the iffy trick to eagerly parse that, get the bytecode, reduce the amount of delazification that's performed at runtime. But it turns out that Facebook.com does a lot of things, a lot of sites do a lot of things conditionally, and it's really hard to produce static bundles that are reusable that all share the same execution characteristics. You saw the around, what was it, 45% number for small scripts?
Yep.
Yeah. So small scripts are another interesting trade-off with cache performance. If we were to bundle all those small scripts together, we'd be able to leverage background compilation, but at the expense of reducing the cacheability and reusability of these packages. Another thing is sending inline JSON as a script tag. This is something we're looking into actively. It's not a huge chunk of our total parse time, but it is like a nice win that we could get by externalizing the JSON so we don't have to run a pre-parse over all of it and just like reduce it to one JSON.parse call. So we'll get you there. And lastly, we could dynamically load code just via like script source tags as we do, but it falls into the same problem with interactions where it's like we're still, if we're dynamically loading it, we're still blocking on it before we can actually show anything. Another solution, I think there was a V8 blog post a while ago about this, is profile-guided IFIs. So this is something that we're currently thinking of doing, is leveraging the samples from the JS profiling API to figure out, okay, so maybe we can't always analytically figure out what code's always going to be executed for all users, but we can find out what code is fairly likely and is on the endpoints that we want to optimize for. So we're thinking of using samples from the JS profiling API to get data from this and test it out in the field so that we could better leverage the available idle cores early on during page load to do more eager parsing. However, more trade-offs. If we want to reuse our JavaScript packages across endpoints, which we often do on Facebook.com, like if you go to home.php, you might get like one JavaScript package that's reused on profile, and maybe some of the same things will be executed, but it's not terribly likely. There's obviously some intersection, which is why we're showing in the first place. But we don't want to do all that extra work on profile for like doing a bunch of things that would only really appear on your feed, for instance. Another idea we had was differentiating our packages based on device hardware tiers, potentially being more conservative with what we eagerly parse on lower end devices so we don't end up wasting cycles, and we're more likely to take advantage of available parallelism and memory on high-end devices. So back to Vlad, he's going to chat about updates on BinAST.
Right, so for people who are not familiar with it, BinAST is binary encoding of the JavaScript AST. So it's not a new language. It's really more like, as I said, like a content encoding for JS. So we've been working on this for a couple of years on and off. Having a binary format has a bunch of advantages. You can scan it a lot faster. It does add additional metadata to function. This is where it departs from the regular ECMAScript spec. So with this additional metadata added to a function, it's very easy to skip over functions that are not currently relevant to you. So that makes pre-parsing nearly free. It also unlocks optimizations like streaming compilation, because you have all of the information you need about a function, what variables it captures, for example, ahead of time. You're able to do like compilation as the file is coming in, which is pretty cool. And one final sort of a developer ergonomic advantage, which I'm going to talk a bit more about later, is that it's a drop-in optimization. This is like switching from, I don't know, gzip to Brotli. It's just something you drop into your compilation pipeline. When Instagram.com deployed BinAST version 1 for an experiment, it was really trivial to wire it up, because it's just an extra stage in generating your JS. So status right now is that we have size parity, but it does rely on external string dictionary. I can talk more about that if people are curious afterwards. But basically, it's to the point where we can do a field trial with it, because the wire size is about the same as plain JS. It's implemented in Firefox. We did 2 versions of it. Both versions are implemented in Firefox, and we're almost ready to do a field trial with it to get some actual field numbers for how much it benefits real users, real Facebook users. We had one Facebook engineer, he's sitting here, Andrew. He implemented the BinAST, this latest format of it, iteration of the format, in V8 in about 3 weeks. It did not take a lot of code. It's not that complex. It's just really another kind of like front end. So what we saw in lab measurements, and we're still in the middle of like evaluating and optimizing it, is pre-parse got a lot cheaper, unsurprisingly. Eager parsing was 25 to 30% cheaper in the current prototype. We think we get more out of it, but this is what we currently have. And then total time spent parsing when loading like a snapshot of Facebook.com for purposes of lab testing was a 40% reduction in CPU cycles spent parsing. And this is, again, not well optimized. We're not V8 experts. It just shows the potential for reducing this overhead. And really, we would love to do a V8 origin trial, maybe on Canary or something, just to be able to get real numbers and see like to show that this actually makes a difference for real users. Also want to talk a bit about sort of like the space in which this BinAST proposal exists. And really this has to do with the hidden cost of developer time. So as I said, I'm part of the browser engineering team at Facebook, which is very unusual because Facebook doesn't have its own browser really. So we contribute code to other browsers' code bases. We do all kinds of optimizations to better match how the platform behaves. But we're really the exception. This is not the rule. So even asking like other companies to maintain separate like desktop and mobile sites is too much for them, just because people don't like a front-end performance team is kind of an unheard of thing in a lot of companies, and even the large ones. So asking people to like really optimize their site or to completely re-architect it to, I don't know, not use inline scripts or to not use scripts that are smaller than a certain threshold is not really realistic. And even if we think back to like responsive web design, the whole promise there was ship the same code base and then just have the same code execute on different form factors, or a desktop or a mobile. That's not really realistic, because if you want to ship an engaging desktop experience, that experience cannot run on mobile. You actually do need different code bases. So that just increases the difficulty of developing for the web. And as we've seen with the Facebook Ads Manager and other enterprise level pages, they accumulate code really quickly because there's a lot of functionality, there's a lot of business logic. So basically the appetite is there to serve more code, but the startup costs are prohibitive. And as I mentioned earlier, one of Facebook's solutions is to do server-side rendering, to actually execute it on the server for every person who visits Facebook.com and send down an HTML snapshot of it, instead of having it execute on the client where the startup costs are prohibitive. So that's all to say that ship less code and re-architect your site is probably the correct advice, but it's not realistic. And we've seen that, like just asking people to like, yeah, you're doing things wrong if you just repackage all of your code and you serve it in this kind of pipeline format, and you do prefetching and like speculative exclusion just right, then you won't have these problems. I mean, it's true, but it's not going to happen. It's not realistic. So I think we really need drop-in solutions like BinAST or other things that can really bring down this startup cost of large sites and enable people to ship actual richer experiences on the web, because we're kind of losing to mobile or to native mobile in a very real sense. So yeah, that's that. Yes.
I guess you said it took 3 weeks to
Yes.
in VA. I guess I'm curious, as far as they're not necessarily stable at the time, right? So it's a moving target. I guess I'm curious, how much time have you spent refactoring
Surprisingly, we didn't break that much. The V8 internal AST representation seemed to be like hilariously stable. While this was done like in a fairly rapid, like caffeine-fueled binge of coding, we did rebase it like several times since like June and didn't really run into any issues. If you're wondering more so about the format itself moving from underneath us, like the IDL format that BinAST uses, moving independent of like what JS engines expect, we saw like a pretty nice like isomorphism between the two for the most part. And this is both in SpiderMonkey and V8. There were no crazy tree transforms we had to do to get this to fit nicely.
Good.
I know this was only a very small part of the problem that you called out, JSON data that you inline in the part of your scripts.
Yes.
You tried using JSON parse directly, where you pass in a string, JSON string byte version of the data as a string literal, which is supposed to be faster than.
Extremely, yes.
And
It's coming.
it's going, okay.
Yes.
Yeah.
It bulk like napkin math numbers, but it reduced the amount of time parsing by like half for the JSON payload.
Can you clarify, because the slides did mention that you can also inline the data in the diff and then get it and then parse that.
Mhm.
Are you talking about that, or are you talking about literally JSON.parse of a string literal in JavaScript, which is super easy?
So we actually compared the two of JSON.parse on a string literal versus JSON.parse on like a data script tag that was just floating, and we found the data script tag was quite a bit faster actually, which was a little bit surprising, but makes sense due to the pre-parser skip. I guess Blink's parser for script tags is a bit faster. Yeah.
Yes. Leszek.
So this is obviously my jam, right? Did the BinAST implementation have streaming as well, or like were the numbers compared on streaming as well?
Yep. So this was done with streaming as well. Arno in the audience implements streaming very recently. Sweet.
And 40% as well.
Keep score.
In terms of, so that was runtime call stats wall time.
Right.
Yeah. Which was fairly close to CPU time after we verified it.
Yeah, just trailing.
Yeah.
Would you guys mind updating runtime call stats to actually use CPU time?
Yes.
instead of clock time, because that's kind of misleading sometimes.
Yeah. Thanks for fixing V8.compile though. That was
That
sweet.
was thank you for that. So the measurements we've done like single-threaded, parsing throughput measurements, and those look good. And then we did like end-to-end. Arno, I don't see there he is.
Yep.
Back. Arno did measurements of like end-to-end performance. This was using a snapshot with 0 network latency, so this kind of sorted in that sense. But yeah, we saw the background script streaming kicking in and all that. One thing that was a little bit surprising is because of like size differences. Because size differences and the shifting in the cost equation, not the same scripts would end up getting background streamed. So that we always have control for that to like do an apples to apples comparison. But if you look at total CPU cycles spent parsing, it's a 40% reduction, which is pretty nice for like a V1 prototype. Yep.
How much do you actually care about the total CPU time? Like,
I care about critical path time, realistically. I mean, this is kind of what this talk's about. That's why it's not a BinAST talk. It's like, we see that the background cores could be better utilized, at least in our case.
So if we would do something like binary SD on the client side, would that solve your problem?
If you could solve our problem by some other means, absolutely. If you want to give us bytecode, that'd be great, even better.
No, I mean, like
if we could
actually like transform source to binary SD on the client side and use that to speed up main thread parsing time.
Well, that's interesting. I have not considered that.
It would solve basically the problems that we have with binary SD.
I see. Okay, I see. So you basically want the background thread to convert the JS text to some sort of binary-like format with the additional annotations necessary to do really fast pre-parsing and really fast full parsing.
Sort of like an IR format for delayification?
Yeah, that would be interesting.
That's interesting.
Exactly.
That would be interesting, sure.
Yeah.
Okay, I mean, that makes it a lot easier, and you don't have to worry about versioning. Are there, in fact, plans to do such a thing? Okay, all right.
Helpful, sure.
All right.
On
I think you mentioned a little bit about the size of the JavaScript. So that's one dimension. The other dimension is when is the JavaScript executed? Like, is it executed before the first content was made, or the largest
I think the microphone might be off.
Yeah, microphone
Yeah.
might be off. I did hear your question though, for what it's worth.
Yeah. So the other dimension is like when is the JavaScript executed? Like, is it before the first paint or the largest paint?
All
Are
the
you
time.
guys looking at that too?
The answer really is all the time, like uniformly from beginning to end. What's funny is, so internally Facebook has 3 stages of loading: time to interactive, display done, and then end to end. And by the time you get to end to end, you have the whole thing pixel complete, and it's at least somewhat interactive. The thing is, like at that point, JavaScript loading does not stop. It actually keeps fetching more resources, and there's also like speculative loading during idle times. There's constantly just like pulling in JavaScript, parsing it, compiling it, executing it. So you just kind of arbitrarily have to like count the CPU milliseconds spent up to some loading point. So it's literally from the first byte that comes down all the way to the end.
So maybe the question is like, are those numbers that we were showing, like 400 milliseconds, etc., what were they for? Where did we draw the line?
Up to that third final point, which ends up, if you have a fast machine, or if you have a very fast machine, it's going to be 3-4 seconds. You have an average machine, it's going to be like 4 to 5 seconds to reach that point. At that point, you can start clicking on the notification icon on the chat tabs, things like that.
Yeah. The reason I was asking was like some of the experiments that I did, I found that a lot of sites have blocking JavaScript. Blocking as in they block the first paint, but they are not really needed before the first paint.
Yeah.
So.
Yeah. So we're not blocking. Our first paint is very fast, and we do serve some HTML that kind of like lays out the frame of the site. So the first paint performance is okay. It's really like ready to use, like ready to send a message, ready to like scroll your newsfeed. That's kind of what really matters the most. And for that, it's that final loading milestone that we look at. Yeah.
So you mentioned the delazification, the lazy compilations, taking about half the time of the main thread compilations.
Yes.
Was that during load or during just general page use?
That was during load.
I see.
Yeah.
So that's a kind of failure of the iffy heuristics in a sense.
Yeah,
No.
I mean that's why we talked about 3 different solutions. Iffies are very hard to get right. Even like as we said, like even if you have like some sort of like average profile of what's likely to be executed, the site has so much branching in it, like what you can actually do. That's very hard to predict which functions should be iffy, which ones should be not. And the problem is that if you over predict, if you say that something will be executed and then doesn't, you're paying a parsing cost, paying a compilation cost, which is double realistically, memory cost. It's very dangerous to overpredict. Is what we find.
That being said, we still are interested in experimenting with like profile guided stuff. The thing is, it's like we are concerned that it's inaccessible to get that like feedback loop going from like users browse your site. We like optimize the site and like get that going with a good enough scale on like most sites. Like I feel like only a handful of sites are going to have the infrastructure in order to do
No,
this.
definitely like when I'm talking about if heuristics failing, I'm talking about it being our failure to do the heuristics properly. We've been talking about doing more static analysis or something along those lines to figure out what stuff's being called. But if it depends on branchiness, then it's
going to be very tough for Facebook. Facebook code changes multiple times a day. So users don't necessarily get updates every day, but doing a static analysis is very hard. So really it needs to be the website authors who are taking like real user behavior and feeding it into the compilation pipeline, which is basically like PGO, but it's like a PGO that runs like multiple times a day. So it's complex.
Is this sort of things that are like library functions that are being like sometimes called and sometimes not? Like it's not clear to me why the execution behavior is different on load.
I think the simplest is features. The simplest example of it is like when I get to the Facebook code, I need to have all the code to render every possible type of newsfeed story. And once you get into it, there's all kinds of crazy newsfeed stories. It could be a video, it could be 3D video, it could be a game, it could be a text post, it could be an image post, it could be a GIF, it could be all kinds of crazy stuff. And because you don't know because you're receiving the code at the same time that you're receiving the data, the code that you receive has to be conservative. You have to be able to like render that first story, regardless of what it is. And then the data comes in, it's like, oh, well, it's a video story. Good thing that I have, the stuff for like muxing the audio tracks. And then people have different configurations and different experiments that they're in and all kinds of stuff. So it's really, really hard to like figure out like what is likely to get executed.
Should we just sit there next to each other?
You guys should come up here. Come on.
How much of the speed up do you think actually comes from the scanner? So like symbol tables, would they help?
Good question.
Yes, we have squeezed a lot of performance out of optimizing the bitAST and V8 scanner. Like just the other day, we got like an extra 5%, 7% just with some creative inlining. The scanner is where we see most of our cycles being spent with it, especially and also Huffman decoding for the most part.
Huffman decoding because we use
because the bitAST V2 format uses like multiple Huffman tables per field in the IDL.
I didn't actually mean how much time you're spending in it, but rather how much time we are spending in the scanner,
yes.
and how much time you're avoiding by having symbol tables, for example.
Yeah.
And
Yeah, it's interesting.
I don't know.
I'm not familiar enough with the V8.js scanner to say. I know you guys did a great job optimizing it a while back. Other than that,
the main reason why I'm asking is because I think it might be might be easier to do things like introducing a symbol table for JS, getting rid of function keywords, disambiguating arrow function and expression list and stuff like this. And we could probably have a thin layer over JavaScript like that.
Yeah.
While all the things that you're doing with like scope resolution and so on, that's much more complicated to make sure that that actually works across browsers and keeps
I wouldn't
working
be
across
surprised.
browsers.
I was doing some comparative benchmarking a while back, and I got something like 18% of cycles were spent just in the scanner code when doing eager parse runs. So that's non-trivial.
Just to clarify from some conversations we've had, because I think I gave you bad information. The prototype you did does include the function skipping with the metadata.
Correct.
So
Yes. Yeah.
do you have a sense of how much that contributed to the speed up risk? Because this thing is what you were talking about, I think would definitely speed up. But since the prototype has the skipping, it'd be good to know what the breakdown was if you have a sense.
Right. So pre-parse is like the big one that it eliminates like disproportionately. A few slides back, we talked a bit about like the full eager parse win, which is with like totally excluding pre-parse, just like both like JS and MinST fully parsing. So I guess the napkin math would be the remainder of like the full parse speed up and the extra speed up that we saw with that 40% number on Facebook.com.
So if you just look at the slides just now, you can see that like the main thread time, a third of the time is spent pre-parsing. So there's a big win there. But it's true that the background threads really benefit from a faster pre-parse. But the full parse also benefits from it.
Yeah.
The thing is, though, that if we can actually move everything off the main thread to the background threads, also the small scripts and the inline scripts, for example, and everything is done before we even start running, then at least you're not actually losing load time there, right? You're just losing CPU time, which is something that you care less about, as far as I can.
One interesting phenomenon that we observed recently when Arnold was doing some benchmarking was, I think he had set it up so that he was not using compression when he was serving the sites. So the small script, these are not benchmark numbers; these are like live numbers. But when he was benchmarking, he would not have compression on, so the scripts look bigger than they actually were. Normally, you make the decision based on the wire size as opposed to the uncompressed size. And what he found was like, okay, there's differences, and it's kind of like shifting the costs around. What he found was like there's a huge difference in terms of like end-to-end load times. We're talking like 20% difference based on what you do with that threshold. So I would say that threshold, like a one-size-fits-all threshold, is probably the wrong way to go. You might want to look at some sort of like CPU power availability to figure it out.
So we're thinking about changing those thresholds anyway, because we're actually moving more work off the main thread, like compilation finalization, for example, is one of those things that's still on the main thread currently.
Yeah.
We're moving that to the background, and it's possible that through that we can actually change those thresholds.
Yeah, I would just say like don't maybe investigate not having just a fixed number, but look at sort of like having like function for like how much, basically scheduling function, because that's what it is. Yeah. So take into account how much is available, how much work there is to be done.
I think long-term just wants.
Yes.
So value is zero.
One thing that it's kind of not put on these slides, like, when we're doing measurements like this, the machine is doing nothing else. It's just loading Facebook.com. There's no other tabs. It's ideal. But that parallelism is always available. You guys have actual parsing numbers from the field, so you might have a better sense of how much parallelism is actually readily available. So.
Yeah, just to add a little bit to I think your question is, does it matter if you're still using CPU time off thread? I've done a little bit of benchmarking on like a mid-range Chromebook or maybe more towards the low end. And when you run the CPU, the Chrome tracing, I can see the giant blocks, which are in the subspan. I can see that there's big delta between CPU time and wall time. And then I can see a lot of the times to steal coming from the background parsing, up to the point where I'm actually considering for low-end devices, we have our lower tier JavaScript. I'm actually considering holding it back from the parsing threads just to make sure they don't steal CPU from the main thread. It's like, I do think it is still a concern, depending on how hardware threads continue to go.
Another way to say is that basically like web pages are still mostly single-threaded applications. Even though you guys do crazy stuff to move the work around, anything that can lighten the load on that main thread and prevent it having its CPU cycle stolen would be a win. Yeah. Are we done for time?
We've got about 5 minutes left.
Okay,
Yeah.
good.
So since we've only got 5 minutes left, could you go into a bit more detail about you mentioned an external string table or external symbol table in binAST?
Yeah, so we basically wanted to, we're trying to do binAST in a way that we would get answers to the critical questions as soon as possible. So that basically means we wanted to front load all the risk. And for that, we were thinking, okay, first we need to get like benchmark. We need to design a file format, got it. Single thread wins, got it. End-to-end wins with a snapshot, got it. Next thing to do was to get field trial wins. So the obstacle to the field trial was that the binAST v1 format, even though it actually had nicer wins than what we have on these slides right now, quite a bit nicer, was that it was a size regression. I forget what the regression was.
Yeah. Also, to be fair, those wins were relative to SpiderMonkey. So
That is
it's
true.
comparing apples.
It
to
is
oranges.
apples to oranges. That is a very fair point. But there were bigger percentage wins. So then Dominic Cooney, another browser engine team member who couldn't attend, he came up with a file format that essentially kind of amortizes the cost or shares the cost by splitting out the shared strings, and there's a lot of shared strings like React strings or like common variable names, things like that, into a separate file that is shared across all of the actual JS files, bin.js files on the site. So it's not the most elegant thing because now you have an extra network request, now you have a dependency between your network requests. But the idea is we can ship this dictionary, and it's actually a pretty stable dictionary. He looked at like how this dictionary would change over a month, and it would not change much at all. It would still remain very effective. We could ship this external dictionary as part of the Firefox installer, and then when the user actually visits a binAST-enabled Facebook.com endpoint, their over-the-wire byte cost would be the same as plain JS. And then we could do like a comparison, like, okay, assuming the size is constant, then what are the benefits for end-to-end loading time? And then, once that shows a win, after that, we'll work on a better file format. Because we're not file format specialists, we're not compression specialists. We just use an external string table and a Huffman encoding to encode the nodes.
On this particular slide, you're basically saying you're loading Facebook for 7 seconds, and 400 milliseconds of that is parsing, right?
Yeah.
How much time is actually idle during this? I mean, are the CPUs actually idle during the 7 seconds?
Benoit can actually speak better to this. I expect when I was doing my benchmarking, I only had the parsing related categories enabled, or like top level, not very idle.
You were probably collecting this on the old side, right?
Yes.
So yeah, we've done a lot of optimization about resource delivery. We've noticed we were hitting some quirks with resource delivery. So our load times, I think, are going to get faster, I think, despite even using a bit more JS and using more React. But from one of the transitions that we're taking from the old side to the new side is where we're doing a lot more of the rendering in React. So we're going to be demanding more from the main thread, unfortunately. So that time will continue to be very precious going forward, even more so with the new site.
It spikes the CPU and it stays spiked for a while. And then once you get past those 3 initial loading milestones, then it starts like dropping off and doing work a little bit more idly.
And so one thing that is relevant is even in the cases where we're missing data, one of the techniques that React is using with React Suspense is we will actually begin the rendering even if we know the data is missing, and that causes JS to warm up, but it does waste CPU cycles because we're rendering components and we will throw away the results. So there's some trade-offs. I don't know that we've hit the right trade-off yet, but we're still continuing that exploration.
And the reason why I was asking is because, like in this case, you're actually probably parsing at like 20 megabytes per second or something like that. Like the mobile that you were showing before, even there you were like parsing at like 4 megabytes per second.
Mhm.
I'm wondering like what kind of download speeds you're expecting on those kind of devices.
It's basically the point here was that the main thread is not network bound, really.
Well, these are, so the 10 megabytes is 10 megabytes uncompressed. So that would be 1 meg compressed that we would be sending down.
2 megs, realistically. Well, like 2 megs. You say 1?
We only have 1 meg.
Yeah.
Oh,
like 1.7.
you're talking about the new site.
Well, so there's a little bit of confusion because some of the numbers that you're quoting are considering what we call our end-to-end milestone.
Yes.
And I think that's what you said you were
Yes.
quoting.
Are you talking about VC?
Yes. And so what normally we target is like our visual completion and interactive. And so in that case, I think I normally look at the compressed size. So it's usually about a meg. I don't know how that maps
I've
uncompressed.
grabbed it a bunch of times. It's like 10 to 12 megabytes uncompressed, and then about 2, maybe like 1.8 or something. But we can just figure it out. Just go to facebook.com, log that. Yeah, not Shakira static, like an actual personal Facebook.
Yeah, that's why you'll hear different numbers, is just because we have different milestones.
Other questions?
Yeah. Okay. Yeah. All right. Thank you all.
Thank you.